Good morning, everyone, and welcome to the session on fundamental properties of cool stars. And if you like stars, I'm sure you like this session. You may have noticed today things are going to be run slightly differently. The first session is going to be, as usual, till coffee time, but the session after that is longer than usual, and then, of course, in the afternoon, you're free to go about anywhere. It's a big hall, and sometimes when you raise your hands for questions, it's very difficult to see, because it's fairly wide. So if you have a burning question and you feel I'm overlooking you, please stand up. Then I'll know you have a question. That way it'll be easier, and also the speaker will be able to see who's asking the question. And of course, please introduce yourself before you ask any question. So we start with an invited talk. The speaker is Saskia Hekker from the Max Planck Institute for Solar Systems Research, and she'll be talking to us about what asteroseismology can do for the properties of stars.
Good morning, everybody. Okay. Thank you very much, Shabani, for this introduction, and thank you very much to the organizers for inviting me here to give this talk this morning, and for all of you to show up at 8:30 on the Wednesday morning. So I will be talking about stellar ages and galactic evolution. What have we learned from asteroseismology? Or in other words, asteroseismology of cool stars, what stellar oscillations can tell us. So what I will do today is I will go through what's asteroseismology, and then I will give you what kind of properties we can learn from that. Before I start with that, I want to make one thing very clear, and that is that asteroseismology is not replacing any other technique. It is a complementary technique, and the aim of today is to make you aware of it, and that you in the future will read astroseismic papers differently and think, hey, I can maybe use this for my own research, or even involve asteroseismology into your research. So that is the aim of today. So what is asteroseismology? So the name comes from Greek, essentially, where aster is a star, and that's also where the E is in there. It's very important. Seismo is oscillations, and logos is reasoning. So what we try to do is we observe the oscillations in a star, and those oscillations give us information about the internal structure of the star, and so we can, in that sense, derive information about the internal part of the star, which is otherwise inaccessible. If you do spectroscopy, photometry, interferometry, astrometry, you get surface properties, which we cannot always get with asteroseismology. For instance, we cannot get an FE on H from asteroseismology. That's impossible. This is a crucial element that we need to get from other observations, such as spectroscopy or photometry. So if we want to look inside a star, this is roughly the idea that we have about what does a star look like. So what you see here is a so-called Kippenhahn diagram, and if I get the pointer doing what I want, yes. So what you see here is the mass. So this here in the bottom is the core. Here we have the surface, is the one solar mass star, and we have H here on the x-axis. So essentially each of these lines here, vertical lines, that is the structure of a star at a certain age. So you can see at young ages we have hydrogen fusion in the core. At some point this turns off, and we have only hydrogen fusion in a broad shell around the core. And this is essentially the subgiant phase, and then we get a very thin shell. We get into the red giant phase, and this is a very quick phase, so we have a zoom here. And then you can see in the end we even get helium fusion if we get to the red clump and the AGB. So what it is that we want to know really if this picture is correct, but also what's happening here at all these edges. So as we're talking about cool stars here, one of the features in this diagram is very important, because we have here in the hatched area, we have convection. And in cool stars, convection is the driving force of the oscillations. So essentially I will be talking today only about stars with convective outer layers. And these are stars cooler than, say, 6,500 Kelvin or so, depending a bit on the metallicity. So this convection area here is very important. We can also look at the stars in a slightly different way. as I would show here. So what I have done here is that you look at 3 different types of stars. So we have a main sequence in the top, a subgiant, and a red giant. And what I've indicated here are the cavities in which the oscillations can reside. So essentially, the parts of the stars from which we can get information. And so we have here in the bluish area, that is the acoustic cavity, and that is where we have waves for which the pressure is the restoring force. And then we have here a red cavity, and that is the gravity area, or the buoyancy cavity, where the gravity is the restoring force of the oscillations. And essentially, oscillations can propagate either in the blue or in the red. And here we have, in each of these pictures, I have this black or gray area, and that is where we roughly see the oscillations for the star. So you can see here in the main sequence, we are essentially sensitive to the acoustic oscillations. Although there are claims that we can see these. I won't go into this. This is a whole discussion in the field. But Hannah Schunker has a poster 276, that deals with oscillations in this cavity of the sun. So if we evolve further the star, you can see that we get more and more sensitive also to this red area, so more closer to the core. And I will come back to what we can learn from that later in my talk. So as I already said, we will study cool stars. These are stars that are cooler than 6,500 or maybe 7,000 Kelvin. So this is a picture for stars for which we also have already Gaia data, the TIGAS solution. We have many more stars, but it's just to indicate you what kind of parameter space I call cool stars. And what you can see here is that here the M-dwarf region is completely missing. And that's very unfortunate. Obviously, they have convection in their outer layers. We also think they have oscillations excited. There are only a few problems. The amplitude of the oscillations goes down as a function of luminosity over the mass. And so we have lower masses, lower luminosities, and so the amplitudes go down in this direction. And also, the oscillations can be inhibited by activity. And obviously, as we have seen already earlier this week, M-dwarfs are very active. So this is more or less the parameter space which I call the solar-like oscillators, and which are the oscillations in the cool stars. So what can we learn? And what I want to show today is that we can learn a lot. So I already told you that we can see something about the stellar evolution and the stellar structure. The next thing, I think asteroseismology can play a big role in studies of exoplanets, because if you know more about your star, you can also know more about your planets. And obviously, if we do it for a large ensemble of stars, we get complementary information compared to spectroscopy and astrometry and so on. And so we can also say something about the Milky Way. And as I go through my talk, I will show you which parameters we can get and what it can do for these fields. So the first parameter that we can get is if we look at the oscillations. So here, what you do, you take a series of photometric or spectroscopic radial velocity measurements. You take a Fourier transform of that, and you remove some of the background signals that we're not interested in, and it looks like this. So this is the normalized spiral density, and this is the frequency in microhertz. This is the typical unit we live in. So this is about 120 microhertz or so. This is a period of a couple of hours. And you can see that there is a clear kind of power excess here. We can model that roughly with the Gaussian, and the center of this Gaussian is what we call nu max. So this is essentially the typical frequency. And we have some scaling relations that were derived by now some 20 years or so ago. And they show that this gets us immediately, if we have the effective temperature, so here already you see we need some spectroscopy or photometry, we can get the surface gravity of the star. So this is the first property that we can get right away. So if we then look in more detail into this power excess, you can see that it's very regularly spaced. And that is called the large frequency separation. So each of these numbers indicates the degree of the mode. So this means the number of nodal lines on the surface. If you look at the radial mode, so indicated with the 0 here, you can see that they are spaced roughly equally in frequency. And it has been shown that this then corresponds to the square root of the mean density of the star. So again, we can get just from measuring this asteroseismic feature, we can get a stellar property. And so just to recap that, is that if we have these two equations, we can measure nu max and delta nu from our asteroseismology. We can get the effective temperature, say, from spectroscopy. then we can get immediately mass and radius out. You can see that this formulation is not depending on any chemical composition, which may give us some deviations, and also it's not depending on any stellar models. And we get masses and radii, say roughly 2, 5, and 2%. So it's not super accurate, but I think it's doing a marvelous job. So we can also include stellar models here. Sorry. So if we say, we do measure, say, the metallicities of the stars with the temperatures, we can also compare our delta nu maxes with a grid of models. This is here done in the case with machine learning, with a random forest, and this gives you the precision of the stellar parameters. So each of these, so this is for 94 stars on the main sequence, and you can see each of these colors gives you a different property, and we can get mass here roughly in orange is to about 4%. The radius here in darker is to 2%, so we get a small further improvement on the accuracies. The big advantage is, for instance, that we can also get the ages out. So if you want to have stellar ages, you can see here, this is the greenish color here, then we get that to about 10%. So this is a big advantage. So we need stellar models, and it's model dependent, but we can also get a stellar age. So I think this is a big advantage that we can do with asteroseismology and the complementary information. So this can, of course, also be very useful for exoplanet research. So what we can see here, we have a transit. So from the transit, we can get the ratio of the planet radius and the stellar radius. If we also have oscillations, as you have in the case of Kepler-36, we can get the stellar mass, radius, and age using the methods that I just explained. And together, we can get the planet radius to a much higher accuracy than what we could do without asteroseismology and just with, say, a spectroscopy. Obviously, there are other ways to get the radii of the stars, such as interferometry, as we heard on Monday evening with the Chara array. So this is, again, it's just a complementary method, but it improves the radii of the planets tremendously. Also, if we can get ages for large numbers of stars, this is very beneficial for Milky Way studies. So here we see work by Victor Zilverguer. He has two chemically different populations, so the low stars that are low in alpha over Fe, stars that are high over alpha over Fe in purple here. And you can clearly see with asteroseismology, we can show that these ages of these populations are very different. What he could also do is, for instance, looking into the age-metallicity relation. It's one of the things that we're looking for in galactic archaeology. And you can see here that we do not have a big trend here. So for this part that he analyzed here, the age-metallicity relation is essentially flat. But again, we need asteroseismology to get ages to an accuracy that we can do these studies. So if I then continue and look further in what asteroseismology can give us in terms of stellar properties, we can look in more detail in the power spectra. So I show here two. This is just the telephone numbers from the Kepler. Again, I indicate the degrees of the modes. And then if you look at these stars, so the central frequency is not too different. It's a bit different, but not too much. Again, this deviation between the large frequency separation, you can see here the numbers 8.00 and 7.89. It's very similar. We don't show any uncertainties here, but it's very similar. But if you look then at here, the region where it's indicated with 1, so we have one nodal line on the surface, and you look at this star, you can clearly see morphologically there's a big difference. What we can do essentially is that we do not see one peak there, we see an ensemble of peaks. And this is, if you think back of one of the first slides when I said you have the blue and the red area, so you have two cavities where the oscillations can be active, and this is actually the sign of that. So these are oscillations that contain information about the outer part of the star as well as the inner part of the star. And we can look at the frequency differences between those peaks. We actually don't do this in frequency, we do this in period, and you can get very different numbers. So you get here 53 seconds, and there you have 96 seconds. The uncertainties are not given here, but they are of a second level or so. So these are significantly different. If we now do this for a whole ensemble of stars, you get such a diagram. So what you see on the x-axis, you see the large frequency separation, and here you see this separation in periods that I just explained. And you can clearly see two different groups of stars. So this bottom group, those are the stars that have an inert helium core, and they have hydrogen shell burning around that. While this group here, this red and orange group, they have already helium burning in the core. And so these stars are typically very similar spots in the HR diagram. So if you do spectroscopy or photometry, you cannot distinguish between them. But the main difference is in the core. We now get information through asteroseismology of the core, and we can separate these two groups. So again, we can get information on the evolutionary state of stars from asteroseismology. So then I have to show the movie. I'll try to make this work for you, because there's more things that we can do. Oh, and start. Yes. So what you see here, the other thing that we can do with asteroseismology, we can look at the rotation of a star. So essentially, we expect all stars to rotate. And if those stars rotate and have oscillations, we can obtain two further measurements. So here you see the stars rotating. Oh, that should continue to play. OK, thank you very much. So what you see is that the frequencies, if you look at these periods here, and when it runs again, you can see that they have slightly different periods. This means that a mode that is running with or against the oscillations, it's essentially a Doppler effect, get a slightly different period. And so we can measure them at slightly different positions in a power spectrum. The other thing that you can see here is that we change the inclination angle. And you can see, due to the change in the inclination angle, we have a change in the amplitude here. So if we look at on the equator, we can mostly see those two. If we look at the pole, and it goes on, then we see that one. So we can also, from the amplitudes of these rotationally split modes, we can get information about the inclination angle at which we view the star. So now go back to the presentation. So we have been using this, of course, to also get this information. And I'm waiting. Thank you very much. And so what we can do with this, we looked at the star. This is again a red giant. And if you look at this power spectrum, so it's again frequency and power, now we have the different numbers that I had indicated so far are now different symbols. So the square here is a 0, the triangle is a 2, and these dots here are the LS1 modes. So these have one nodal line on the surface. And if you look in detail, you can see they're slightly split. So these three are containing different information from the core. But then this very small splitting here, that is rotationally splitting. And so what we can do, we can measure that. And we measure the rotational splitting. And you can see we get here kind of V shapes. So if you now model this and say, look, I expect my star to be a solid body rotator, you can do that. Then you get this shape here. Well, that's clearly not a V. I think we agree on that. But if you assume a fast core, say 10 times faster than the surface, you can qualitatively reproduce the observations. So with this, we have been able to measure radial differential rotation in stars, which is very important because in most stellar models, rotation is not included, and we actually have no clue about the angular momentum distribution and evolution. And so this gives us observational clues of what the rotation profiles are. If we do this for a large set of stars, which is on the way, then we can learn something about the evolution of angular momentum in stars. As said, we can also look at inclination angles. And again, here I have an example of that where it's a planet involved. So this is a red giant. Here it has two eclipsing planets. So we know the orbital axis of the planets. And then we also had asteroseismology of this star. And what we could do is we could really measure the inclination angle. And we found that the spin axis of the star is actually like this. So we have obliquity in this case. And we have learned something about this using Rossiter-McLaughlin effects yesterday. So there are other ways to also measure this. But this is, again, a complementary way of doing it and telling us that this star is oblique. The importance of this is that this may hold clues of how planetary systems are formed. So this could only be the case if we assumed a third companion orbit, and this was indeed found using radial velocity. So this, again, this obliquity measurements can give us clues on the evolution of the planetary system. So if we then continue and we look more and more closely at the power spectra that we've been looking at, we can also see that there are, there are small variations in the frequency. So we have this regular pattern, but we also have some slight changes to that. And we can measure these changes, so you see essentially these changes here. Given each of these colors is again a different degree of the mode, and we can fit some functions through this. And this function is a function we call this glitches, and two of the main things that are going into this is that we have a small abrupt change in the stellar structure that gives this, and these changes are due to the helium second ionization zone and due to the bottom of the convection zone. And the periodicity that we can measure here tells us roughly where are these glitches or these sharp changes happening. And so here in blue you can see in acoustic depth expressed, we can see where the helium second ionization is, and in red we can see where the bottom of the convection zone is. So we can have actual measures of where these kind of abrupt changes in the stellar structure are. So continuing from that, because we are sensitive to the helium second ionization zone, we can also see if we can measure helium. In all these cool stars there are no helium lines, and so we cannot directly measure helium. But if we are sensitive to the helium second ionization zone, we can. And this is a study by Verma et al. And here you see they have changed the helium abundance, and they looked at the amplitude of the signal. And you can clearly see that there is a trend. And so in principle, we can get also information about the helium abundances through asteroseismology. So what we can do, we can go even further. What we have done so far is we've always said, okay, we measure oscillations, we have frequencies, which stellar model would fit best to those frequencies? We can also turn around this question and say, look, we have here frequencies. What stellar structure would explain those frequencies? And so we have tried to do this, and we have tried to what we call stellar inversions. So this has been done for the sun since decades, but for stars this was so far not possible. First of all, because in stars we find less oscillation modes, because we can see only a point source, while for the sun we can obviously resolve the disk and get more higher degree modes. The second point is that for the sun, we know the mass and radius very, very accurate. For stars, even for 16 A and B, which are very close stars and there's lots of information about them, there's still some uncertainties in the mass and radius. So these things has to be folded in, and so last year we were able for the first time to get inversions from this star, from these two stars, and so that you see here is the radius, so you can see we can get kind of the first 1/3 of the star, so the center part of the star, and here you can see the sound speed difference. So essentially what these points indicate here is the difference in the sound speed between a best fitting model and what we observe. And so now we can say here in 66A we can see that there's a slight deviation, while in 66B we are very consistent. So this tells us then that there's something missing in the models or should be changing in the models and so on and so forth. So these were the first two stars for which we did that. There's a poster by Earl Bellinger where he presents the same results for about 20 stars and also some indications of what kind of physics we may want to change to mitigate this problem and actually get better models and better justified models with the physics included that is needed. The future of asteroseismology is quite bright. So we have here Corot was a French-led satellite that has been running from 2009 to about 2012 and has observed very different fields in the sky, and so there is astroseismic data from that. Kepler obviously has been looking at for 4 years at one different spot, and the NASA people have been very clever to turn this into a K2 mission when the stability was not ensured any longer, and so it's also a whole track along the ecliptic where there's now astroseismic data. Both of these, certainly Kepler but also Corot, are reasonably faint. As you've heard by George Ricker on Sunday, the TESS mission has been successfully launched and is now started the observations in the southern ecliptic hemisphere, and so these are much brighter stars, an all-sky mission. So again, there's a lot of astroseismology that can come out of that. It is obviously, it's targeted essentially for exoplanet transits, but I think astroseismology will be a very big part of this mission as well. And then we have here song indicated, so all of these missions that I show here are photometry, but it sometimes can have advantages to do spectroscopy and measure oscillations in radial velocity. And so this is what SONG can do. So the plan is here to have 8 different telescopes. At the moment, I'm sure there are 2, and I think there are plans for 2 more to build a network all around the Earth so that we do not have any day-night gaps. And here in the further future, we have Plato. Plato is an ESA mission that will be launched somewhere in 8 to 10 years from now. And that will again have slightly brighter stars than Kepler and K2. There's a plan for a step and stair phase. So again, many stars will have asteroseismology from that. So if you want to include that in your own work, I think there are plenty of opportunities in the near future. So I hope I have shown you the power of asteroseismology for cool stars, and I hope I conveyed some of the enthusiasm that I feel for this field and that we can get real nice stellar properties. Thank you for your attention.
Thank you. Thank you very much, Saskia. And I'd like to open the session to questions, and I see one right there.
Rob Jeffries, Keele University. Thanks for a great talk. You mentioned an uncertainty in age of 10% quite early on in your talk. Could you just sort of clarify whether that's a 10% age that doesn't depend, a 10% error that doesn't depend on age, or whether it's actually that younger stars have a better absolute age precision?
So what I showed you is a precision, not an accuracy. So obviously, if the star grows older, you carry on the uncertainties that you've built into your models because it's a model-dependent age from early on. So I think...
I suppose what I mean is a star that's 1 billion years old, is the age uncertainty 100 million years? Or is it 1 billion years, and that it's still 1 billion years if your star is 10 billion years old?
I'm not fully sure I understand the question here.
I suppose I'm asking, is the age precision of 10% independent of age?
Yes, I would say so. But I have to say here that we only looked at the main sequence. So this value doesn't really show that. But if you go up to the red giant branch, I don't think it's very much more age dependent. Maybe if you go on further, it is, but that is not where we've looked.
We have another question there.
Ansgar Reiners from University of Göttingen. Thank you, Saskia, for this excellent introduction. Can you let us know what is needed to get astroseismic data in M-dwarfs?
So first of all, you have to have a not too active M-dwarf because the activity will diminish the oscillations. And then you need, so the amplitude goes down anyways because of the luminosity going down essentially. So you need to have very, very high accuracy in either your radial velocities or in your photometry to get it above the noise, which will probably mean long observations. The other thing that you have to keep in mind is that the frequencies moves up or the period goes down. So what I showed here was a power spectrum of red giants. So you have about an hour or a couple of hour period. So you can do with one observation every half hour, say, like Kepler did. If you go to the sun, the period is about 5 minutes. So half-hour observations won't bring you anything. If you go further on to M-dwarfs, I think the periods will go shorter again. And so you have to have very rapid observations as well. So all these things added up make it very difficult. So if you want to do it with Carminus, you will have to have very, very short exposure times to be sensitive.
Okay.
Hi, Rachel Austin from the Space Telescope Science Institute. That was a nice talk. And I had a question about the plot that you showed where you did the inversion for the stellar case. Can you explain why you're sensitive only to the inner part of the interior of the star and not the outer part of the interior of the star?
This is because we can only observe low-degree modes. So this is based on modes with 0, 1, 2, or 3 nodal lines on the surface. And they have their turning points quite deep inside the star. And that's why we're sensitive to deep inside the star. If we were to observe higher degree modes, those modes are sensitive much higher up in the atmosphere, and so we can also do that. We have done a test. This was for rotational inversions, but that was if we had the modes with degree 10, we could do rotational inversions at say, about 0.5, radius, fractional radius of 0.5. So it is just the fact that we have only the low degree mode, that we have sensitivity only to the core.
Okay, thanks.
The question there, and then the last question there.
David Phillips, Center for Astrophysics. Lovely talk, nice introduction. You talked about activity in M dwarfs suppressing the oscillations. Can we turn that from a bug into a feature and do time domain asteroseismology and look for activity? Is there a possibility of learning something new from some time domain signal?
I'm not sure how, because in the time domain you see the spots, of course, as well, the activity. So I'm not sure if you want to see small variations on that. So I'm not sure I fully understand your question here.
I was hoping that maybe the amplitude of the P modes might tell us something different about the activity than the mean photometry.
I'm not sure, because obviously here we have, it is a transform of what we see in the light curve. We actually do look at the light curves at the moment, also in my group. And because if you have short time series, as we have for some of the test data, you will not have the frequency resolution, and obviously all the signal is also contained in the shorter time series. That works, but the success rate is a bit lower. So I am doubtful about it, let's say it that way.
Thanks.
It's the last question right there.
Thank you. Hi, Saskia. This is René Heller, Max Planck Institute for Solar System Research, Göttingen. I'm approaching light curves from a planetary exoplanet point of view. I'm just wondering, and pardon my ignorance, I don't have a feeling for the frequencies or frequency shifts involved. Do you think it's possible to detect stellar companions or a stellar companion to a given star, which has asteroseismology measured, by measuring the frequency shifts of this given star over, say, years?
So with solar-like oscillators, these are driven by the convection, and by that fact, it's a stochastic oscillation. So it is not that we look at a delta function for the frequency, but it is something that has width, so it's a Lorentzian width. So in those things, it will be very hard because you have a natural variation already. However, Simon White, if I look at Sabani for the names right, has done this actually for A-star. So A-stars are classical pulsators, so they're hotter, they don't have the convective envelope, so they have a different driving mechanism. The oscillations resemble a sinusoid, so you get a delta function in your Fourier spectrum, and he has been measuring companions to this from the shift in the frequency. So yes, it's possible, but for these stars, it is much more difficult because of the stochastic nature of the oscillations.
Thank you.
Thank you, Saskia, and thanks for the wonderful questions from the audience. And we could